Okay, problems 9 and 10 are next. They're fairly quick ones, so we'll do both of them together. Problem 9 asks, for an elementary reaction, an experiment is performed with a large excess of B. So A plus B goes to AB. We put in a whole lot of B, which means that by the time A gets completely used up, the B concentration's hardly changed at all. Under those circumstances, it seems intuitive anyway that A is going to look like it goes straight to AB, right? The B concentration isn't changing, so it's going to look like a first order reaction. Is that true? And if that's true, what would happen if we plot the logarithm of A as if it were a first, it's in fact a second order reaction, right? What would happen if we plotted the log of A versus time, or if we plotted a 1 over A versus time, what would we get? Well, over here is the answer. First of all, this business of putting in a huge excess of one reactant in a higher order reaction is called flooding. It's a standard trick among kinetics people. And it basically reduces the order of the reaction. If one reactant isn't changing, it's basically a constant, then it looks like the other reactant is reacting on its own. Let's see how that works. We actually have an expression for the way that the concentration of A changes. Let me blow that up a little bit more. There we go. Changes with time for the second order reaction with two different reactants, A and B, right? And here's that expression. But now let's suppose that the B concentration is enormous compared to the A concentration. Let's suppose it's 1,000 times bigger than the A concentration, so the A concentration is just negligible. In that case, here let me erase some of these lines, these red lines here, and I'll put them back in as I'm going through it. First of all, that's going to mean that this B over A here is huge compared to this other thing over here, which means that this term is the only one that's going to survive, right? This term's going to be negligible. Also, this term is huge compared to this term, which means that that A0 is also going to go away. And when that happens, when both of those things happen, notice that then we've got a B0 divided by a B0, so the B0s are now going to cancel out. And that means we're going to have in the denominator down here 1 over A0, which is going to turn into an A0 on top. And e to, well, that A0 is going to go away too, e to the B0k times t. And so when we're done, by the time we're done with all that stuff, I'm trying to keep my notes in order here, so I'm going to erase all that stuff. There we go. By the time we're done with all that stuff, everything has reduced itself to just this form. And that's the equation for a first order reaction if the rate constant isn't K, right? This is a second order rate constant. It doesn't have the right units for a first order rate constant. But B0, the flooded concentration times a second order rate constant would have units of seconds to the minus 1, right? A second order rate constant has units of molar to the minus 1, seconds to the minus 1. So if you multiply it by molar, you're going to get units of seconds to the minus 1, which is the same as the units of a first order rate constant. So this B0 times K value is the effective first order rate constant for this flooded reaction. Also, it turns out that if you then look at how B changes with time, well, the A0 concentration is negligible, the B0 concentration, the A concentration is negligible for that matter, and you just get that B is constant with time, which is, of course, what we started out saying. And if you look at what happens to the P concentration, you can also see that you get behavior that looks like a first order reaction if the rate constant, if B0 times the true rate constant is taken to be an effective rate constant. All right, that means that a plot of log A versus time would give a straight line, even though it's a second order reaction. I say here a plot of 1 over A versus t would be curved. I think that's actually true in this case. That's right. Yes, it is true in this case. because the 1 over a versus t plot, the straight line for a 1 over a versus t plot is for a different reaction, right? It's for 2a goes to product, not for a plus b goes to product. So even though this is also a second order reaction, it doesn't have a 1 over a type plot, straight line plot, the way this one does. So this is the wrong reaction for a 1 over a plot. And that is it for this problem. Let's go on to problem number 10 then. All right, this one, let me give myself some space here. I'm gonna bring up some empty space here. And so the problem in this case is just to write some rate equations for a mechanism. It's a pretty straightforward, pretty short, pretty simple problem. That's why we can do it here straight out. So I have this three-step mechanism, pretty simple. It says write the full set of rate equations for each species present. So let's do that. So first of all, I have 2a goes to b. I have b goes to c plus d. I have a plus c goes to d, k1, k2, and k3. So dA dt is then going to be equal to minus 2 times k1 times a from this reaction minus k3 times a times c from this reaction. And that's it. It only appears twice. dB dt is then going to be equal to plus k1 times a. Actually, I made a mistake here. For this term, from this reaction, that should be an a squared there, right? Because there's two a's there. Sorry about that. And that's true here too, right? That's why I caught it. The b here is the result of a second order reaction, plus because it's a product. It disappears here, and that's the only other term that's going to come in, so k2 times b. dC dt is then equal to, C appears in just these last two, it's going to be equal, it's created, so it's k2 times b, and then it's destroyed in the next one, minus k3 times a times c. And finally, d is equal to, appears just in these last two again, it's going to be k2 created times b plus k3 times a times c. And that is that for that problem. This was just an exercise in writing rate equations for mechanisms.